All right, chapter 9, antiderivatives. So far in this course, we have been doing what's called differential calculus, which means that we've been doing some sort of differentiation or taking derivatives, which is mostly what we've been doing for these chapters. We're now going to look at going backwards. And so we're going to be looking at differential equations and thinking through the opposite, taking the inverse, which is the antiderivative. So most of our equations have worked with, have involved rates of change, and those equations are called differential equations because they contain functions and they're differential quotients. Basically, that's just these examples here, the derivatives that we have found, okay? Differential equations are basically our derivative equations, because when you look at this first one, dy dx is equal to 2x, it's just saying the derivative of y in terms of x was 2x. So what we need to figure out was what was the original function in terms of y. That process is called antidifferentiation. It'll find the antiderivative. So if y prime is equal to f of x, then the solutions to these equations, these differential equations, are called antiderivatives. Okay, we're working backwards now. Okay, and the process of finding the antiderivatives is actually called integration, and what you would call integral calculus. So there's differential calculus and there's integral calculus. And so for whatever reason, I think it's chapters 9 and 10 talk about this process as anti-differentiation, but really it's integration or integral calculus that it would be called at university. So I don't know why the textbook refers to it only as anti-differentiation in the first couple chapters here. But regardless, we're going to be doing integration, and it is denoted by this kind of long-looking skinny S symbol, and that's called the integral sign. So just like dy dx is telling you to take the derivative, this integral sign here would be saying you need to take the antiderivative. You need to integrate and work backwards. Okay, so let's think about this one. Write an antiderivative of f of x is equal to x squared. So this is talking about f of x equals x squared being the derivative. This is called a differential equation, and we're working to find its solution, which would be the antiderivative. Okay? So I want you to hit pause and think about what would have been the original function. Think backwards for a minute. Okay, so when we take the derivative, we take one off of our exponent. So if x squared is my derivative answer, then the original guy had to have had an x cubed. And then in order for my derivative answer to have no constant, then I need something out the front that I can multiply that 3 by, so I'll get an answer of 1. So hopefully we thought through some of that. And so the antiderivative to this could be y equals 1/3 x cubed. Now the beauty of this is that we can actually check our answer and see if we got it right. So then if I take the derivative of what I just said was my antiderivative, I would take 1/3 times 3, which is 1, and then I would get, maybe we'll write that out just for sake of notes. Okay, 1/3 is your constant. You take your 3 down, x to the power of 1 less, which would be squared, and then that would give me x squared. So then the question is can we write any other functions that have a derivative of x squared? Is there something else out there that would also work to give me that derivative? So what if I wrote y is equal to 1/3 x cubed minus 10? Would that work? Well, yes, because the derivative of a constant is 0. So, or what if I wrote y is equal to 1/3 x cubed plus pi? Well, yes, because pi is a constant as well. So anytime that I have this antiderivative process that I'm trying to think of, I'm going to have to realize that I could have any kind of constant tucked on the end because the derivative of a constant is 0. So we're going to have to remember that little extra piece. And so what we do is when we think about this as a general antiderivative, when we write the antiderivative of a little f, we use a big F. Okay, so if they haven't said f prime of x, they've said that the derivative is x squared, so my differential equation, then the antiderivative is the capital letter of that from the original, to form the original equation, sorry. And so we would write 1/3 x cubed plus c, c being my constant. And so on all of these, we're going to have to add on a plus c because the derivative of a constant is 0. Okay, so if f is an antiderivative of little f on an interval, then the most general antiderivative of little f on that interval is big F of x plus c, okay, where c is any constant. All right, so this process of antidifferentiation, also called integration, and really that's more what it would be called at university, does not determine a unique function, but rather a family of functions, each differing by the others from some constant, okay? And so this is called the indefinite integral of f of x. We will get into definite integrals, but that's later, okay? So what we're looking at is this family of functions that all differ from some constant, and they're called the indefinite integral, and it's denoted by these symbols, okay? So the funny looking S, okay, the funny looking S, this integral S, integral sign, means take the integral of the differential equation of f of x with respect to, okay, with respect to x, okay? So the symbol is the integral of f of x with respect to x, that's the dx part, okay? So it's that's just a command saying this is what you need to do in math notation, okay? The integration process that requires you, so we were looking at a polynomial of f of x is equal to x squared. Well, actually, the process for this polynomial in general, x to the power of n, is just to increase, okay, is just to increase your exponent by 1 and then divide each term by that increased exponent. So if you think back to, we had f of x was x squared, the antiderivative of that was to take the 2 and add 1. 2 plus 1 is 3, and that's what we divided by. So you get the 1/3 x cubed. So we will use that for all our polynomials. It's a very handy little property of antidifferentiation. So just remember that integration is the inverse of differentiation, and we're working backwards now. Okay, so a few properties of antiderivatives. So if you were asked to take the antiderivative or to integrate 1 in terms of x, you know, so if you had some sort of constant, it could be 5, it didn't have to be 1, but you would just know that he had to be x. So think about if you had to take the derivative of x, you would get 1, okay? And then some constant c, so that we will always have to add our plus c, okay? Okay, if you have some sort of constant coefficient in front of your function that you're trying to take the antiderivative of, you can actually just put it in the front, take the antiderivative of your function, and then multiply your k constant in afterwards. Another property is if you're adding or subtracting two functions that you're asked to take the antiderivative of or to integrate, you can separate them. okay, and then add, subtract them afterwards. All right, we're just going to go through a whole bunch of general antiderivatives here and think about what they would be. So if I have a function of 0, the antiderivative of that would have had to have been a constant, right? So if y was equal to 5, the derivative of 5 is 0. So we're thinking backwards now. So the derivative of 1 would have been x plus c. The derivative of x to the n, so we just formed that one. That was x to the power of n plus 1 all over n plus 1 plus c. Don't forget your plus c. So cos, so you have to think about who has a derivative of cos. Sine has the derivative of cos, so sine x plus c. Then what happens if the argument has a constant with it? Okay, so would it just be sine kx plus c? Would that be okay? So let's think about this down here for a second. What happens if I had sine 3x plus c? What would be the derivative of this? Well, the derivative of sine is cos 3x, the same of the argument, but remember, don't forget your dinner, we would multiply by that inner derivative, 1/3, plus 0 would be the derivative of c. So we need to add in a 1 on k in front there to make it so that we would have no coefficient on the actual derivative. Okay, moving along. Sine. So who would have a derivative of sine? Is it cos? Does cos have the derivative of sine? Almost. Cos has the derivative of negative sine. So the antiderivative to get sine would be negative cos would have the derivative of sine plus c. Similarly here, we would have to have negative 1 on k cos kx plus c, so similar to 2 lines back. And then think who has the derivative of secant? Tan had the derivative. Who has the derivative of cosecant? Well, cotan has the derivative. Oh, I forgot my plus c. Oh dear. Make sure I had it on the other ones. Okay. Cotan has the derivative of negative cosecant squared. So we would need to have negative cotan x plus c. Who has the derivative of a secant tan? Secant has that derivative plus c. Cosecant cotan, that would be negative cosecant x plus c. Now these two here at the bottom here are from chapter 8, and we're not going to cover chapter 8 this semester till the end of June, only if you're interested in it. But I'm just going to write them out so that the chart's filled in. So the antiderivative of 1 on x is actually the natural log, ln x, but the absolute value of that, because x has to be positive for a log function, plus c. And then e is a funky guy, kind of like pi, and that we would look at that in in chapter 8. So these are just to fill in a chart if you're interested in it, but again, these last two ones were from chapter 8. Okay, so we're not going to test you on it this semester. So don't worry about it. It won't be a part of your assignment either for chapters 9 to 11. Okay, so now the next section is a whole bunch of questions for you to try. I'm going to come back in video number 2 and go through them, but before you hit go on video number 2, I would really encourage you to try as many of these as you can. Don't forget your plus c on the end and see how it goes. So you're just going to work backwards. So remember, if it's little f of x, then you need to write big F of x as the antiderivative function. Okay, see you in video 2.